Welcome to IT.Solution, your total network, system, firewall, and security partner.
All right, let's dive right into this. Welcome to today's Explainer, where we're going to unpack one of the most fascinating and honestly foundational mechanics of networking, how your data actually travels across networks without turning into total, utter chaos. We are looking directly at ITN Module 14 today, specifically focusing on the transport layer. So if you've ever stopped to wonder what exactly goes on under the hood of your network connection to keep everything perfectly organized, well, you are in exactly the right place. Let's get started. But first, think about this for a second. Right now, you probably have a web browser open with, 20 tabs, an email client pulling down new messages in the background, and maybe you're even streaming music or sitting on a live video call. All of this data is flowing into your single computer through one single network cable or Wi-Fi connection at the exact same time. So, how on earth does your computer juggle all of this without accidentally, dropping a piece of your video call into your email or a chunk of a web search into your Spotify stream? How does it keep all that data perfectly sorted?
Well, to answer that, here's our game plan for today. First, we'll meet the transport layer. Second, we'll uncover the magic of port numbers. Third, we'll look at TCP, our reliable workhorse. Fourth, UDP, the speedy courier. And finally, we'll talk about choosing the right protocol.
Okay, Section 1. Meet the transport layer, the grand organizer of your network.
And this brilliantly illustrates exactly what we're talking about. The transport layer sits right smack in the middle, between the application layer up above it and the internet layer down below. Honestly, you can think of it as the ultimate mailroom clerk for your device. See, the lower layers, like IP, they're just concerned with getting a packet from one computer to another. They don't actually care what the data is. But the transport layer, it takes over the second that data arrives at your computer. It acts as the bridge, grabbing that network data and handing it over to the specific software applications running on your screen. It's responsible for tracking all your individual conversations, segmenting the data, and multiplexing, which is really just a fancy word for interleaving different communication conversations onto the same network at the exact same time.
Moving right along to Section 2, the magic of port numbers, the secret weapons of networking. So, how exactly does this mailroom clerk know which application gets which package? To understand how data finds its exact destination inside your computer, we have to talk about a socket. A socket is just a combination of three things: a source IP address, a transport protocol, and a port number. Let's use a real-world analogy here. Think of the IP address as the street address of a massive apartment building. That gets the data to your computer. But your computer has lots of applications running, right? Those are the individual apartments. The port number is the specific apartment door. By combining the street address and the apartment number into a socket, the network knows exactly which specific application should receive that incoming data. It's brilliant. And these port numbers aren't just random. They are heavily structured by IANA to keep data clean. We have our well-known ports, ranging from 0 to 1023. These are reserved for common universal services. For instance, web traffic usually hits port 80 or 443, and email might hit port 25. Because these are well-known, your computer always knows which door to knock on for a website. Then we have registered ports, which go from 1024 way up to 49,151. Those are assigned for specific user applications you might install, rather than universal internet services. Breaking the ports down into these ranges guarantees the right data gets to the exact right app every single time, no mix-ups. All right, Section 3, TCP, the reliable workhorse of the internet.
Now that we know how data finds its application door, let's look at the actual delivery protocols carrying those boxes. TCP is incredibly thorough. So, the crucial point is understanding this rigorous four-step process. First, TCP establishes a connection. It actually requires an exchange of messages before a single byte of data is sent, like a formal handshake. Second, it segments the data into manageable chunks and sequences them. It literally numbers every single piece. Third, it demands an acknowledgement. It sits and waits for the destination to say, "Yep, I got packet number 1. And fourth, if it doesn't get that acknowledgement, it will retransmit the lost data. TCP is absolutely the meticulous registered mail of the internet. It completely guarantees delivery. But because it has to wait for all those acknowledgements, it carries quite a bit of overhead, using a 20-byte header just to track all this information.
Which brings us to Section 4, UDP, the speedy courier and our lightweight contender. But what if you literally don't have time to wait for acknowledgements? What if you just need sheer, unadulterated speed? Enter UDP.
UDP is the exact opposite of TCP. It is blazing fast because, well, it simply doesn't care about the rules. It's connectionless. It doesn't bother saying hello. It just starts aggressively throwing data at the destination. It has massive speed and incredibly low overhead, using a tiny 8-byte header. Why so small? Because there are 0 acknowledgements. It doesn't sequence the data, and it absolutely, positively does not resend lost data. If a packet gets dropped along the way, UDP just shrugs and keeps throwing the next datagrams at you. It's a best effort delivery protocol. Honestly, it's like a fast, carefree courier on a bicycle weaving through rush hour traffic.
Finally, Section 5, choosing the right protocol. So we have the slow, methodical perfectionist in TCP and the reckless, lightning-fast courier in UDP. Which one do we use? Now, what's really interesting about this slide is that neither protocol is inherently better than the other, not at all. They just serve entirely different real-world purposes. TCP is connection-oriented, highly reliable, and features flow control. UDP is connectionless, best effort, and has minimal overhead. Your network absolutely needs both of these to function, and the choice depends entirely on the specific tolerance of the application you're using at that exact moment.
Just look at how these common applications map out. On one side, we have TCP. When you open a web page or send an email, you're using TCP. Why? Because if a single packet of data is lost in an email, the entire message could be corrupted. You need TCP's meticulous reliability to ensure every single letter arrives in perfect order. But look over at UDP. Voice over IP, DNS resolution, video conferencing. When you're on a live video call, you need speed above all else. If a single frame of video drops, you do not want the network to pause the entire call to go back and retrieve it. By the time it did, your conversation would be hopelessly out of sync. The app is completely tolerant of a little lost data. It prefers to just keep the video moving forward. And that is exactly where UDP shines.
And that brings us to the end of our explanation on the transport layer. We've seen how the mailroom clerks route data, how port numbers act as our apartment doors, and the eternal balancing act between TCP's guaranteed delivery and UDP's blinding speed. So I'll leave you with this. Knowing what you know now about sockets and ports, how many invisible TCP and UDP connections do you think your device is secretly managing in the background right at this very second? It is a perfectly orchestrated chaos, and now you know exactly how it works. Catch you next time.
Thank you for watching. See you in the next episode.